Hi again everyone, Chris Tisdell here. In this presentation I'm going to continue my series of videos on partial differential equations. Now in this video and the previous one we've been looking at solutions to the inhomogeneous wave equation in one spatial dimension. Okay, so here C is a constant, H is some source term that's inputting force or displacement into the string or the system. Phi and psi are the initial position and initial velocities. Okay, now this is the solution to this inhomogeneous problem 15 and 16. Now in the previous video we looked at the case when these two functions, the phi and the psi, were both 0, and we proved that this satisfies the 15, 16 with phi and psi identically equal to 0. Okay, and I said at the end of that video that I would go the other way. I would start with this and end up with this. Okay, so that's my objective of this particular presentation. Now to keep things simple, I'm just going to imagine phi and psi as being 0 functions here. So we won't worry about these terms, we'll just want to get to this. Okay, now I'll come back to this a bit later and give it a bit more meaning. Okay, so for the purposes of this presentation, phi and psi are both identically equal, so we don't care about those things, we just want to get that from that. Okay. All right, so let's consider a point in the xt plane. Let's consider this triangle here. So let me just draw a simple sketch. Now essentially the way we're going to come up with this formula is to basically look at a double integral of 15 over this special triangle, and then we're going to apply a theorem from vector calculus called Green's theorem. So let me show you how it all works. Okay, so here here's our point x0, t0. This point so will correspond to where we have equality here on this line. So that will be x0 plus c t0, comma 0. This will be x0 minus c t0, 0. Okay, so this region then is this triangle or delta set here. And the boundary is just the 3 line segments. Okay, so if we take 15, let's take a double integral over both sides where we're integrating over this triangular filled region. Okay. Sorry, let me get those pages right. There we go. Okay, so we integrate over the filled triangle, and then we can apply Green's theorem. So Green's theorem essentially relates, at least in the plane, in 2 dimensions, relates double integrals with line integrals over the boundary of the 2-dimensional region in question. Okay, so if we apply Green's theorem from here to here, we get the following, and essentially what we're doing is we're going to integrate this expression over this line segment, then this line segment, then this line segment, and add them all up. Okay, and that's going to be equal to this double integral. Okay, so if I, let's say, this line segment be L0, this line segment be L1, and this line segment be L2, then I've got 3 line integrals to calculate. Now I'm not going to calculate them all, I'll calculate 2 of them, and the third one's pretty pretty similar. So L1's very easy, L2's a little bit of work, and L2's almost identical to the case of L1. Okay, so let's consider this expression on the line segment L1. Now along L1 you can see that basically it's just a line that's parallel to the x-axis. So the t variable is not changing at all. So basically t is 0 and dt is 0. So if I wanted to evaluate this line integral, what I do is I replace dt with 0, so that term's going to disappear, and I can evaluate that term at t equals 0. Now, what is this? This is just the negative of that. And remember, for this proof, we're imagining that, or just assuming that this is identically equal to 0. So this would be 0. So the line integral over this segment is just 0. So pretty simple. Okay, so let's have a look at the line integral over this segment here. Now, over that segment, we have equality in here, okay? So x equals that, t is between 0 and t naught, and if I take the differentials here, I'll get dx equals negative c times dt. So what I can do is take this expression, replace dt with negative dx on c, okay, so that term has gone to that term, and replace dx with negative ct, so that has gone to that. Okay, so now if I take a common factor of c out, c is just a constant, remember, and I can sort of factor this into a dot product form. Now this is a special dot product. This is a gradient, okay, it's a gradient or grad of u, and you can think of this as just some sort of dr where r is a vector. Okay, so here we're taking the line integral of essentially a gradient function or a gradient field. Okay, now there's a special theorem for evaluating line integrals of gradient fields. It's called the fundamental theorem of line integrals. And essentially it just means that this expression is independent of the path. So the path, how we get from one end of the line to the other, doesn't matter. Okay, and essentially this just depends on the endpoints of the line segment. So you can see in here, I'm moving from here to here. Okay, so essentially this type of line integral only depends on the endpoints, and it's essentially u evaluated at the endpoint minus u evaluated at the starting point. Okay, that's essentially the fundamental theorem of line integrals. Okay, so this will go to this, and what is this? Well, okay, that is just our initial condition or our initial position. Remember, we're assuming throughout that phi is identically equal to 0. So this term is 0, so that disappears. So I just get this. Okay, so I've done two line integrals. I got 0 for the first one over this line segment. I got c times u over that line segment. Last one is this line segment. I'm not going to do it, but if you basically follow the same steps as in the line segment L1, you'll come up with the same result. Okay, it's not difficult to show. So if I take my double integral, add my three segments together for this line integral, 0 plus c times u plus c times u, then I get this. Okay, so if I just divide out the 2c, I get the following. So now this is just the same as this expression here. Okay, here I've got an x naught and a t naught, etc., but it's the same expression. Okay, so that is how you derive the solution to this problem when phi and psi are both identically equal to 0. And it relies on Green's theorem. And you can see some videos of Green's theorem which I have from a course in vector calculus. You usually see it in a Calculus 3 course at university. Now, I told you at the start that I'd get back to this formula a bit more and try to interpret it. Okay, so what does it mean? Okay, well, this is a linear PDE, and so if you have two solutions to linear PDE and you add those two solutions, then the sum is another solution. So let me put that into context for this problem. If I cover this up and I cover the h up, okay, so imagine h is 0 here. This is your homogeneous wave equation with standard initial conditions. What's left here is D'Alembert's solution, or D'Alembert's formula for the homogeneous problem. Now, if I cover this up and cover those up, okay, imagine phi and psi is 0. Then what you can see here is a solution to the non-homogeneous problem with 0 initial position or displacement and 0 initial velocity. Adding those two types of solutions together gives you the solution to the whole problem, 15 and 16. Now, I hope you've enjoyed this presentation. I hope you found it useful. Please join me for more videos in the future. And I just wanted to say one thing before I sign off. I've been really sick over the last 3 weeks, and it's been really nice to get words of encouragement and get well soon messages. You can probably see it in some of my videos. I look terrible, and I found myself making lots and lots of mistakes. So thanks for putting up with me, and thanks for all your wishes, and I am slowly starting to feel better. So thanks a lot.